So hopefully you've had a wee bit of a chance to look at the definitions that are on the first page for those different enthalpy changes. If you have skipped past and just gone to the video, please do actually look back over those definitions now, because I'm going to be using lots of those terms such as electron affinity, atomization enthalpy, bond association enthalpy, and if you're not quite 100% on what those words and terms actually mean, you might find this a wee bit more confusing than it needs to be. So having looked at those definitions, we're going to look now at how do we use them to make this calculation work. Remember, we're trying to just calculate the lattice enthalpy, the enthalpy change when you break apart one mole of a lattice to make into gaseous ions. So, as mentioned above, the standard lattice enthalpy is a useful enthalpy change. Remember, you can make work out things like hardness and solubility from this lattice enthalpy. The problem is it can't be calculated directly. It's not very straightforward to actually do an experiment where you break apart a lattice and do nothing else. Therefore, we need to use Hess's law. So if you remember Hess's law, a way we can work out unknown enthalpy changes by using kind of a sum using other enthalpy changes. We're going to be using that here. So we need to solve a Hess cycle. So I know it's in the notes here, but it's going to be easier to follow if I just do it from scratch. So remember, the change I'm trying to work out here is going from a 1 mole of a solid lattice. I'll just stick to sodium chloride. And I'm going to work out how it breaks apart to form a gaseous sodium ion and a gaseous chloride ion. That enthalpy change is known as the lattice enthalpy. Shorthand would be delta lat H standard. So that's the change I'm trying to work out. I've just learned on top of this page, I can't work that out directly, so I can't do an experiment to work out what that value is. Therefore, I need to use Hess's law. To set up like a Hess cycle to maybe try and work out what this change, how I could calculate this change, I'm going to put down at the bottom here the elements in their standard states, because that's a kind of a common thing to put into a Hess cycle. So there's going to be sodium as a solid, and half a mole of chlorine diatomic. Half a mole because I have to make a balance with what's at the top here is only 1 chlorine, so I have to make 1 chlorine overall here. And then I'm trying to think about how I can make that fit into the cycle. So looking at the left hand side, NaCl as a solid lattice, then comparing it to the elements in the standard state. Basically what we've got there, if I do an arrow in this direction, that would be the enthalpy of formation. Remember, enthalpy of formation is making 1 mole of a compound from the elements in the standard states. That is actually an enthalpy change I can look up in a book, a data book, and get a value for it. So it might be quite useful. So that is going to be delta H of formation. And then the other change here is going from the elements in the standard states to the ions as a gas. I'm going to call that delta XH. So I'll come back to that delta XH in a second. But if you think about the cycle I've got now, this would actually work if I have values to work out the lattice enthalpy. Remember, Hess's law says the path you take for a reaction doesn't actually affect the enthalpy change for it. So I can do via a number of steps and it'll give me the same value as going along the reactions, like in a straightforward sense. So to work out this enthalpy change going from left hand side to right hand side, I would need to flip an arrow here. So I need to change this one to point down. So I need to flip the sign of the enthalpy of formation. And then I can just follow the arrows down, add those two numbers together, and that would get me the lattice enthalpy, just like we did in Hess's law in AS2. The one catch here, which actually makes this a wee bit more involved, is, as you might have guessed, delta XH isn't actually a single enthalpy change. So there's no enthalpy change on the first page of these notes that tells you can go from sodium solid and half a chlorine gas into sodium plus and chloride minus. That's not actually one enthalpy change. What we actually have got here is a number of enthalpy changes happening together. So if you think about it, what's happening here, if you look at the sodium is going from sodium just an atom to sodium plus, so that's going to be an ionization energy. It's also changing from solid to gas, that's going to need to be a change as well. The Cl2 is going to individual chlorine atoms, that's breaking apart some chlorine bonds, and it's also going from neutral chlorine to chlorine minus. So we've got like a number of changes happening at once here to represent delta XH. So if we come back to the notes here, you'll see that we've got the same diagram printed out for you. Just to explain again what I was saying there, the top arrow shows the lattice enthalpy, which we're trying to work out. The left hand arrow is the enthalpy of formation, which we can easily look up. The problem is with the right hand arrow, delta XH doesn't actually represent a single enthalpy change. You can check that on the first page if you want. delta XH actually represents a combination of a number of enthalpy changes. In this case, it's actually 4. It might be slightly different depending on the compound, but we've got 4 enthalpy changes represented by that arrow here. Here are the steps you actually need to do, and this might take a wee bit of slow thinking by yourself to work it all out, but I'll try and explain it. The first thing I need to do here is I need to convert sodium solid into sodium gas. That change there is known as the enthalpy of atomization of sodium, like we saw on the first page. However, once I get into the gas form, I need to do one other thing to it. I need to make it into sodium plus. That's referred to as the ionization energy of sodium. Sodium gas going to sodium plus, gas plus E minus. At that point, the sodiums are fine. The chlorine, I first of all need to break it apart because it's diatomic here. I need it as an individual atom. So that's known as the enthalpy of atomization of chlorine because I'm making 1 mole of chlorine atoms. Once I've got the 1 mole of chlorine atoms, I need to make them negative, and that, if you remember from the first page, is known as the electron affinity. You're going to add an electron to chlorine to make it a chloride ion. So that single arrow there is actually representing 4 individual changes to get from the bottom to the top there. Now, that doesn't actually change too much in terms of Hess's law. I know most of the Hess cycles we've looked at before have involved just kind of 3 arrows. There's no rule about Hess's law, but it can only involve 3 different things. The rule is that the root doesn't matter. So the root can actually involve lots of different steps to get from left to right, and it still counts. And we can actually try and show that down the bottom. So what we've done here, we've replaced, instead of the delta XH arrow, we've replaced it with the 4 changes we said actually are represented by that arrow. So the first thing is atomization energy of sodium, then the ionization energy of sodium, then the atomization energy of chlorine, and then the electron affinity of chlorine. So those 4 changes are now in this cycle. So this cycle will actually work. It's actually completely mathematically correct. I would flip that delta HF arrow and then just add all these numbers together, and that would actually get me the last enthalpy. The only reason we don't keep it like this is obviously you can see it's a wee bit cluttered, a wee bit ugly. And the cycle is correct, but trying to keep it in this kind of triangle format we're used to with Hess's cycle means it kind of looks a wee bit confusing, a bit hard to use. So to make it a bit more straightforward, a bit more user-friendly, we actually show it kind of like an energy level kind of diagram, a bit like this on the next page. This is kind of the form we will use in this topic. The name of it kind of changes. It's no longer called a Hess cycle. It's known as a Born-Haber Cycle, named after the 2 scientists who came up with representing it like this. That's Haber from the Haber process, you might remember. So this might look a wee bit overwhelming for now. I'm just going to tell you to take on face value. This is actually the same thing we saw on the previous page. It looks a lot different, and I will talk through how you form this, but we're just representing what we've got on this page in this kind of clunky looking diagram here, and we're going to show it in a slightly more user-friendly format. So I could talk you through how this diagram looks as it's printed, but I think you actually will get more use out of it if we actually go from scratch and try and work out how we actually form this ourselves. The other reason I'm going to do that is that actually can be a question in the exam. They can give you a big blank space and say, draw the Born-Haber cycle for sodium chloride, and you'd be expected to be able to do this. I'm not actually recommending you try and rote learn this, because there's too many examples to rote learn. You do kind of need to be able to understand and work out how to do this from scratch. It's not as hard to look though, as it looks though, I promise. So, how we form this Born-Haber cycle is as follows. What we start with at the bottom is our ionic compound. So if I do a wee level here first, I'm going to say that is sodium chloride as a solid. So one wee difference first of all about these Born-Haber cycles is instead of just having random equations and arrows, we're using energy levels. So that line for sodium chloride is trying to represent the energy value or enthalpy value for sodium chloride. A bit like enthalpy diagrams we looked at before, we're kind of got a scale here. If I go up, I'm putting energy in, so going to a higher energy level. That would be showing an endothermic process because energy has to be taken in. If I'm doing an arrow down or a level down, it's kind of showing an exothermic process because energy is being given out to make the energy drop. So the first thing you're going to put in is the energy change you're going to calculate, which is last enthalpy. The last enthalpy is endothermic, so the arrows are going to go up. And I'm going to do a new energy level, and I'm going to show on that what I end up with. The last enthalpy is the energy to break apart 1 mole of a lattice into gaseous ions. So it's going to go to Na plus G and Cl minus G. and we should always put the state symbols in to make it super clear what we're talking about. It's a good idea to label your arrows as well to make it clear what you're actually talking about. Gonna call this H lat for last enthalpy. So that's the first arrow I'm going to put in. The second arrow I'm going to put in is the enthalpy of formation. So that's forming your ionic lattice from the elements in their standard states. So that's from sodium as a solid and half a mole of chlorine gas. In this case, it's exothermic. I said in most cases formation values are exothermic. You can get a few examples which are endothermic. We'll not worry about that for now, but we said slightly exothermic. So delta FH for that one. So what I've started with are kind of the simple enthalpy changes from this cycle. If I go back to one on the previous page, we've got our last enthalpy drawn and we've got our formation enthalpy drawn. What we need to do now to finish this off is show all the enthalpy changes I said that made up the rest of this cycle. So all the individual changes here. So going from my elements in their standard state, the first thing I'm going to do, the order doesn't actually matter that much, but the standard format would be to start with the sodium. So first thing I'm going to do is split it up from a solid into a gas. So new energy level, it's endothermic to do that. And just keep everything the same apart from sodium is now in the gaseous state and chlorine hasn't changed. It just stays, sorry, that should be Cl2, stays in Cl2 and as a gas. On my arrow I'm going to show it's the atomization energy. And that represents that first change. Once I've got it in a gas form, I need to now make it into the ion form because that's what I'm trying to aim for. So that involves the first ionization energy of sodium. So a new energy level. Again, it's endothermic for removing an electron. So delta IE1. And we're changing it to sodium plus as a gas. Chlorine still hasn't changed, it's a half Cl2. One important thing that you can lose a mark for if you forget. Now the electron, I know we normally just imagine it's being removed. I am going to keep it on this line though. I'm going to need that electron later on for the chlorine step, so I need to keep that electron on this line. So remove that electron from sodium, it's now sodium plus. So sodium's now all set. It looks exactly the same as it should at the end of the last enthalpy. So now I need to turn my attention to chlorine. To get chlorine correct, I need to break it apart into individual chlorine atoms, and I need to make it into a chloride negative ion. So first thing I'll do is break it up into individual atoms. Up here. So it's going to keep sodium's going to be the same. So Na plus. It's now chlorine atoms, and just one mole of them because I have a mole of Cl2. The electron is still there. I'll need it in a second. That enthalpy change is kind of running out of room here. It's the atomization energy of chlorine because I'm making one mole of atoms. It could also be, depending on what they gave me in the example, it's half the size of the bond association enthalpy. Maybe look at that in a wee bit more detail later. They could give me value for bond association enthalpy, which would be breaking apart one mole of Cl2 to make 2 chlorine atoms. I would just have to half that value to get that to match up with this cycle. Almost there, I've got chlorine as neutral gaseous atoms. Need to make it into a chloride ion, so I need to add that electron I got from sodium into the chlorine. That's going to be an exothermic process because the first electron affinity is always exothermic. And that actually completes the cycle. So starting from my elements, I can go this route and that takes me to Na plus and Cl minus. And going by this route, I also get the Na plus and Cl minus. So it is similar to a Hess cycle, it just looks a wee bit more kind of stretched out in these energy levels. So again, it'll make more sense to actually use it in terms of the maths, but it's just putting those enthalpy changes in the correct order, in the correct format. Just going back to your notes there, so you should have just the same diagram I drew, just printed out for you there. Because this has come up as a question where you do have to draw this in the exam, we've got some pointers here about some things to just be aware of. I haven't mentioned them as I narrated that drawing there, just to show you them in your notes. First thing is that the arrow directions matter. So in the Born-Haber cycle, the arrows show two things, the direction of the change and also whether the change is exothermic or endothermic. So what I mean by that is it shows the direction of the change. If we look at last enthalpy is going from the ionic solid to the gaseous hands, so the arrow has to go from there to there. So it's going in the correct direction of the change. That's one thing. However, the up or down of the arrow tells you whether it's exothermic or endothermic. So in this case, that change is endothermic. So we have to draw the arrow going up. So that's what's mentioned down here. For the last enthalpy, it's described as the enthalpy change when 1 mole of an ionic compound is converted to gaseous ions. Therefore, the arrow has to go in that direction, NaCl to Na plus with Cl minus. And also, it's endothermic, so it must go up. So there's kind of two things we worried about, your direction and also your start and finish point. As I mentioned, state symbols do matter. So you have to put those in the on the lines of your cycle. A very common mistake is to forget the electrons, particularly with ionization energies. Don't just leave it as Na+. You've removed the electron, it's still there because we needed to put into the chlorine at the end of this cycle. So we needed to leave that on the line. And the last thing is just the thing I mentioned in passing. They can give you, for the chlorine or the diatomic element, either the value of the atomization energy or bond association enthalpy. You have to kind of manipulate it the correct way. Again, this might be a wee bit hard to kind of grasp until we actually look at an example, but if we look at the change for chlorine, it's going from a half Cl2 to 1 mole of Cl atoms. That change in itself is atomization because you're making 1 mole of Cl atoms. It's also the same thing as half the bond association enthalpy, which would be 1 mole of Cl2 going to 2 moles of Cl. So you might have to do a wee bit of multiplying up or multiplying down to get the value correct. So that is the Born-Haber cycle. Again, we haven't gotten near calculation yet, but we're very close to it now. We'll look at it in the next video. Remember, all it is, it's trying to show the root around this reaction. We're trying to work out the last enthalpy here, which we can't calculate directly. So we need to use a combination of enthalpy changes for other changes we can make in the cycle. And this is just the way we represent it. So you might have to do a wee bit of practice. You can just grab a sheet of paper, see if you can just do this with your own hand. It kind of helps it get into your head, showing all the individual changes you get from the bottom right round to the top.